To show how to create a strut-and-tie model in cast, I've created this simple example here of a simply supported beam with a point load, not exactly in the middle. And this will be simple enough, I hope, to make this short, but also cover basically all of the important features in cast. I'll start by opening cast and clicking on the new project. I'll give this project a name, example, STM, put my name as the designer just for bookkeeping purposes. And right now it will ask me the D region thickness of our project, which in my case is 300 millimeters, so the thickness in the out of plane direction. So 300. Since this is an example, I'll use commonly used values for compressive strength of the concrete and the rebar yielding stress. For the tensile strength, we won't use it in our calculations, but if you want, you can use the default value in cast. It won't be used in any purpose for what we are going to do. So I'll do everything based on the millimeter units, the international units, but if you want to, you can right off the bat choose the US units, and then all those things would be in kips, inches, and KSIs. But for the sake of this example, and also will be easier when we go into finite element modeling of this beam, I'll use the millimeter, the international unit version. So the first thing we need to do is to define the outer boundary of our system, which in our case is our beam. So 600 millimeter high and 2000 millimeter long. I'll select this construct outer boundary, and when you open cast for the first time, this snap to grid button will be turned on, and you see that your mouse will snap to this grid. If you want to change this grid, you can click on this button right here, construct grid points, and make it closer together or farther away. Since our geometric size of our beam are multiple of 100, I'll keep it as it is. And this is honestly only important when defining this outer boundary, because it's a little bit harder to change this later on, so it's good that it snaps to the grid in this point. So I'll start clicking here and then go into 600, 2000, going back to 0 and closing the boundary, and it detects my boundary. I'm gonna make it zoom a little bit better, and that's our beam. So right now we can already start creating our strut-and-tie elements. So because strut-and-ties processes the process of using strut-and-tie to design or to check a structure or member is very iterative, so it changes a lot. So in this case, I will start with a very simple strut-and-tie model, which is basically going to connect the point load to my supports, and then I'll connect that with a tie. So I can select here construct STM elements, and for now, for example, I will disable this snap to grid, because changing the exact locations of the nodes that we will create is easier than changing the boundary. So I'll select the edge, and cast recognize that I want the edge, so we will see that it kind of snaps to the edge, which you can also disable if you want, but I like that. So I'm not going to worry a lot about the position of everything, because like I said, it's easier to change. I'm gonna press Control to make straight lines. So I'm going down, and then I'll select somewhere in here, go down again to the edge, in here something similar, and go back. So this is my first iteration of the strut-and-tie. The nodes are not located in the right place, so I can right click the nodes and change the coordinates of the nodes through here. So I'll put this 100, which is the location of the centroid of the bearing plate from the edge of the beam. My load I know is at 700, so I'm gonna copy this to this node as well, and this node here should be 100 millimeter away from the edge. I'll copy this and put it on this one as well, and this one should be 100. So these two nodes on the bottom one, the ones that are gray, and this is why it is important to click on the edge, so cast know that this is on the edge, so it's a gray node. I'm gonna make this a restraint, and also this one a restraint. And you can change the size of these elements by clicking on these arrows right here. The first arrow is the size of the font, such as N1 and 2. For example, if I click here, you see that it diminishes. The second one is the thickness of the nodes and the lines. I like it thick. And the load and support size, for example, this green restraint size, you can also adjust it in here. So okay, so this is our first iteration. And for the vertical location of the point nodes, the bottom one is a little bit easier because it should be at the centroid of your tie, of your reinforcement that goes here. So for example, if we assume that we are just going to use one layer of reinforcement, and we consider that, and I have that in here, consider that the minimum clear cover for a being not exposed to the weather or in contact with the ground, which I'll assume is this case, should be about 1.5 inches. It could be even 3/4, but let's consider 1.5 inches for this case, plus 1/2 inch for the thickness of the tie of the stirrup that will go around the main reinforcement. Let's say 2 inches, which is about 50 millimeters. So we can consider that this node is 50 millimeters, and this one is also 50 millimeters. So for the vertical location of this node, there's no method, like official method, that you should use, but a good recommendation that I've seen is to use the thickness of the compression block of the concrete, which it's a very common, very known equation from design of reinforced concrete beams. You will need to know the area of the reinforcement that you want to use. So like again, you have to make an estimate if you want to use that. In this case, for the sake of this presentation, I'm just going to use the same distance as the bottom tie, which will be 50 millimeters from the top. So right now we could already run our model. Actually, I will need to put the load. So the load for this is 400 kilonewtons, right? If we go back, yeah, 400 kilonewtons from the top here. So if I click right here to run this design calculations, first CAST will ask me to save. So I'm going to make this example 3 because I already have some other files in this folder. And then right now it will give us an error, a big error, by the way. So every time this big error occurs, it is, I would say, 90% of the times or even more, because your system is unstable. So in the hood of CAST, it is trying to create a finite element model of this structure, and if that errors occurs, usually because your model isn't stable enough. So remember that this is a truss model, and these nodes here do not transfer any moment, so this is basically a hinge. So in this model as it is right now, we don't have any type of horizontal restraint to the movement of this system. That's why it's not being able to solve. So if we just create a, I would say, dummy element here and restrain that and try to run again, you will see that CAST calculated some loads for our struts and our tie, but if we right click this element, we will see that the force value in here is 0. So this element is not changing anything in terms of the structural capacity of our beam. It is just there to make the system stable for finite element purposes. Like I said, we can change the size of this text. And right now, CAST shows us what is a strut and what is a tie. So struts are usually blue with these dashed lines, and ties are orange with a constant line. So the next thing that we should do is to actually define our struts and our ties. So if we go right here on the top, this first button here is to define the general properties. This is what we have done when we started our project. This is the window that asks us the compressive strength of the concrete, the yield strength of the tie, etc. Right next to it, you will find the buttons to define the concrete struts properties, the tie properties, basically non-pre-stressed reinforcement ties are our ties, and then the node properties. So let's start by the struts. So this will vary based on what code we are using. For this purpose, for this demonstration, I'm going to consider that we are using the ACI. So the ACI differentiates the struts that are on the boundary of the element and on the edge of our element. And I think there is a good picture in the code, if I can find it pretty easily. Here. So the boundary struts are the ones that are basically in contact with the edge of the element, and the interior struts are struts that are not in contact with the edge. So for our case, for our strut-and-tie, all of our struts are interior struts, and this is important because when we go into the section of the ACI code that defines the strength of the elements, we find that first of all the elements, struts, ties, or nodal zones, have a factor that should be multiplied to account for design loads. And if we go into and I have that in another document to make it faster, if we go into the table that defines that factor, we see that for struts, ties, nodal zones, bearing areas, basically everything related to strut-and-ties, this factor is 0.75, and you can find that on table 21.2.1 in the latest code. And in cast, we define that by this strength reduction factor. So this is that phi that should be applied to all of the elements in this strut-and-tie. So let's add this. And then the second factor that we need to apply here is what cast calls the efficiency factor. If you go back to ACI, we will see that for the struts, the strengths are basically a modified version of the compressive capacity of the concrete times the area of the strut. If we look into this modified version of the compressive capacity of the concrete, we see that we need to multiply that by 0.85 times beta C times beta S, where beta S comes from this table and beta C comes from this table. I'm not going into details about code related things related to STM, but usually you find that the beta C is 0.75 and beta S is 1. So when you multiply that by 0.85, that gives you 0.6375. And this is why when you go to calculate your beta S, you need to differentiate what is a boundary strut from an interior strut that I showed earlier. So for our case, interior struts, that usually gives us a 75. You should check it in a real project, but usually it gets a 75, and I'll consider that to move through that quickly. And this beta C should be usually is 1. So when you multiply that by 0.85 and all those betas, this gives a 0.6375. And every time you do some change in anything, you need to click this modify to actually apply. So there we have it. All of our struts should be interior struts, and since we only have one type of strut, we just need to create one. We can even modify this to say like interior strut and then modify. Can I change that? Oh yeah, okay. Interior strut 0.63. Now for the tie, there is a very similar approach. If we go back to ACI, right here it gives a strength of the tie, which is basically just the area of the tie times the yield strength of the tie. And if we remember that 0.75 should be applied to both struts and ties, this is what the strength reduction here means. Now there is this yield over strength factor that we do not recommend you using, and leave it as 1. And I'm going to put this as tie, and I'm going to edit. I can always change this, but this yield over strength factor, we can look at this figure, for example. It basically accounts for this extra capacity, let's say, of the reinforcement after it has yielded due to strain hardening purposes. But usually we don't design for going into post-yield stuff, post-yield regions. So I recommend leaving that as 1. So in here we also need to specify the amount of reinforcement that we will use in that time. So in order to do that, you can look at the amount of force that tie needs to resist, and based on the the area of the different reinforcement that you have, you can calculate how much you will need here. What I like to do, I think, at least to me, is faster, is to first of all assign that tie, clicking this property type non-pre-stress reinforcement tie, and then the tie that I've created. And right now, before I even run it, it says that it's already overloaded by a 1.25 factor. And if I run it again, it shows me that overload here. So I know that 3 bars, number 19 won't do it. So I increase that, modify again, and this should be good. So now it's 0.9. So I know that 4 number 19 bars should be enough, and I can even try different combinations using more bars of lower diameter bars. I can play with different number of layers and see what works best. So this is what I like to do. So in here now, the only thing that's left is to define the thickness or the width of the struts so CAST can calculate the stresses of the struts to see if they are good or not in this design. So in order to do so, we can use this image here from also in the ACI code. You can find this image, which basically says that the width or the thickness of the strut is the bearing plate times the sine of this angle, and plus the thickness of the tie times the cosine of the angle. So if we go back to CAST, this angle right here I calculated previously. This is about 40 degrees. So this would be, and this is where we specify this width. This will be 100, and the 100 comes from the length of our bearing plate, so 100 millimeters times sine of 40 degrees plus 100, and the second 100 comes from the thickness of our tie, because our tie is in a 50 millimeters from the bottom. So we assume that the thickness of the tie is 2 times that. So 100 times cosine of 40, and that gives us basically 141 millimeters. And while we are here, we can also assign this as a concrete strut and our interior strut that we defined earlier, and also do the same for this one, interior strut. And to calculate this, again, this would be 100 times sine of this angle here is about 22.6 plus 100 times cosine of 22.6, which would give us about 131 millimeters. Let's also do this for these small elements in here, assign them as interior struts and make them 100 millimeters, and this 100 millimeters, and again the last one 100 millimeters. And also let's make this tie the thickness that it has, so 100 millimeters. So I'll just save that and run again, and now we see some color coding of the stress ratio of each of these elements. Of course, greens are good stress ratios. You can see the stress ratios here. 0.6 times the capacity of this strut element, 0.68, and our tie is about 94% of the capacity of these ties. So the last thing that we need to define here is the strength of the properties of the nodes. And if you look into ACI in the strength of the nodal zones, we have again a modified version of the compressive capacity of the concrete multiplied by the area, and this equation looks pretty much the same as for the strut capacity, but this beta n is new. So beta c is usually taken as 1, like I said, but again, in a real project you would actually check the value of beta c, but usually it's 1. And beta n is based on the type of the node, which has 3 types. The first type is when you have only compressive struts going into that node. The second type is when you have 1 tie on that node, and the third type is when you have at least 2 ties going into that node, and they need to have different directions. If you have 2 ties but they have the same direction, like a tie in here, it's still considered as 1 tie. So based on that, we have this different versions of beta n, which we need to multiply by 0.85 to get the value of the efficiency factor. CAST already comes with ACI, CCC, CCT, and CTT nodes, which yield correct efficiency factors if your beta c, if this beta c value is 1. Like I said, if in a real project it's not 1, then these values do not apply, and you would have to click this user define and manually calculate it. But for our sake, we're considering that beta c is 1, and we can simply let's make this CCC modify. Let's make this CCT and use the CCT version, and then CTT and use the CTT version modify. Okay, so to apply these nodes, we right click on the node, and here on node type we select the type that we want. In this case we have 2 compressive and 1 tension, which would be a CCT. Same for this one, CCT, and this one would be all compression, right? Compression, compression, and compression, CCC. And now if you run, we should have all of the different elements configured properly, and these results should be final for our model. If we wanted to, like I said, now that we know the area of reinforcement that we need, and since we have a good margin, it's most likely we won't need to update that. We can go back and calculate a more refined distance of this node based on the actual clear cover, based on the actual diameter of the bars. The same thing, we can use that equation that I showed before to get a more refined version of the vertical location of this node. But since those should be minor refinement, that shouldn't change much of the results that we are shown right now. So I won't do it in this demonstration. So this simple strut-and-tie model should be good to go if it wasn't for one problem, which I made purposefully in order to show what I'm about to show. The problem with this strut-and-tie model is that the angle of this strut is less than 25 degrees. And ACI has a clause that specifies that the strut should be at least 25 degrees. If I manage to find that clause right here. So right here, clause 23.2.7. So the angle between the axes of any strut and any tie shall be at least 25 degrees. And like I said before, this is about 22 point something. So the reason why is because strut-and-tie should be used. It can be used for slender beams as well, but it is more effective if the beam is deep. And if you need to use a very shallow strut with a very shallow angle, usually it might mean that that element is not that deep, so you should not be using strut-and-tie as much. So that's why that clause is over there. But we can, and that's also to illustrate that if you have such a shallow element, it is likely that your stresses from your point application won't go exactly directly to your support here on the right. So because of that, you need to break your strut. You need to consider that this stress will actually go somewhere here, and then it needs to be picked up by a vertical tie, and then it needs to go down to the support that way. So I showed that. I did that in this case to illustrate the case where we need to consider a tie in the middle here, and use this strut-and-tie to design that. So I'll save this file and I'll open the example 2, which is already done that. So this model is exactly the previous one, with the difference that I broken this strut that was going straight to the support into two struts connected by a tie. And then I used the same rules to define the widths of each strut right here. And this strut of the same as the tie, bounded by the thickness that it has to the edge of the element. So this is to illustrate how we can use this strut-and-tie to design our stirrups or our vertical reinforcement in an element. So if we run this system, we should have the results of each element, and everything should pass in this case. And for the tie here, I haven't specified anything because I just created, and we see that it needs to sustain a load of 133.3 kilonewtons. So what we can do here, first of all, there is a to consider the spacing of that tie. We can look at this image here, for example. So if this is our load application point and we consider a 25-degree angle, we can consider that that tie that we have in our model will bundle all of this vertical reinforcement here in just that tie. So when we figure out what is the amount of steel reinforcement that we need for that tie, we can consider that this is going to be the spacing that we need to distribute them. So this will help us define the spacing of our vertical reinforcement. So in here we have that this spacing is the available length, should be the distance between these 2 points minus 2 times the vertical distance between the points times the tangent of 25. So if we do that to our model, the distance between these 2 points should be 1900 millimeters minus 700, which is 1200 millimeters, minus 2 times the vertical distance should be 500, and then tangent of 25. That gives us 733 millimeters that we will use to bundle all of our vertical reinforcement. So vertical reinforcement, especially in beams, are usually two-legged. It can be even three-legged, but in this case let's consider it's a two-leg. So we will consider one hoop as two area of steel because we have 2 legs. So if we know that we need to resist 133 kilonewtons, 0.3. So this is the force we need to resist. I can use for example the bars, let's say number 4 bars, which is 129. I will have 1033 megapascal of stress. I know that my bars can only resist 400 megapascals times 0.75, which is the strength reduction factor. So that tells me that I need 3.44 bars. So 4 bars, right? And since we are considering that each bar has 2 legs, I can divide that by 2. So I need actually 2 bars. And the spacing that I had was 733.7 divided by 2. That makes it about 366 millimeters of spacing. So if we define that as let's create a new reinforcement for that. Let's call this the vertical reinforcement, and have that as, you see that it doesn't go all the way to number 4, so we can use the user defined to specify an area that we want, and number 4 is 129, and we will use 4 because it's actually 2 hoops with 2 legs each, so 4. So click that. Oh, I'm sorry, I I created it on top of the existing one. So let me go back to, let me cancel that and create a new one, vertical reinforcement. And I'll add that as a different one, change this to 129, modify that. Okay, so now if we apply that to this tie vertical reinforcement, this should pass now with a stress ratio of 0.8, and we now know the spacing of our tie reinforcement. So this will be our final design for this case. Of course, we only designed the main reinforcement and the vertical reinforcement. We now still need to make sure that the effective length of the ties are in place. We need to make sure the cracking reinforcement, the minimum crack reinforcement for this beam is satisfied based on the code. So the other aspects of the code, we can read it in the code. We don't need cast for that. But in terms of what we use cast for, in terms of strut and tie design, I believe I covered everything.